Lesson 9.5 is called alternating series. It's a very specific kind of series. You can see in the write-up right in the beginning, this -1 raised to the n power or something in the same family will show up in each of the alternating series types. They have their own tests, and not only that, but we can determine not only convergence or divergence, but absolute or what's called conditional convergence, and I'll get to that when we get to that later on in the chat or in the lesson. It says, so far, most series you have dealt with have had positive terms. In this section and the next section, you will study series that contain both positive and negative terms. The simplest such series is an alternating series, whose terms alternate in sign. For example, geometric series. Okay, so first of all, something to remember is if there is a product. Now, technically, there's a product and a quotient in here. We could break it up in 3 different ways. But whatever monomial is raised to the n power, then it can be broken up and each of the components can be raised to the n power. For example, -1 could be pulled out, leaving 1 over 2 to the n. Technically, it's 1 to the n over 2 to the n, but we know 1 to the n theoretically is 1. Is an alternating geometric series with r being -1/2. Alternating series occur in 2 ways. Either the odd terms are negative or the even terms are negative. So we're going to look at a series. We're going to let a sub n, meaning just a term in the series, be greater than 0. Then 2 types of alternating series exist, right? Either the odd component will be, or the odd element will be negative. So if I plug in 1, I get -1. If I plug in 2, I get +1. Or if it starts here with 1, then we might have an even number. When we plug in 1, we get an even exponent rather, starting with a positive and then alternating from there. This will give you a convergent series if the limit as n approaches infinity of the last element is 0, but also the terms are decreasing for all n. The terms are decreasing. At a sub n plus 1 is a smaller number than a sub n. All right, so let's prove the convergence or divergence of this series. Twofold. The very first thing we need to do is determine, is the limit as n approaches infinity of a sub n. Now, a sub n, if you look back up here, is the non-alternating piece. So if I removed this, I removed the alternating piece, I would be left with 1 over n. That's bottom heavy. It's growing so that the 1 divided by infinity is going to give you 0. So yes, the first condition is met. Number 2, what would happen if I plugged in n plus 1, which would be the next term, and compared it to 1 over n? We already know a larger denominator means a smaller fraction. Now, I don't need to put the equal sign here, but it is true, right? That would fall into the right category. So both conditions are met. Therefore, this is convergent. Okay. Keep moving on. Remember, you can pause this at any time if you want to try them on your own. First, we're going to look at the limit as n approaches infinity of the non-alternating piece, which would be 1 over n squared plus 1. This denominator is growing to infinity, and 1 divided by that is 0. First condition is met. The second condition is to compare n plus 1 plugged in for n compared to the original. Well, certainly, if this was, say, 5 squared plus 1 is 26. That would make this 6, and 6 squared plus 1 is 37. So this denominator is larger, or is a larger denominator than this denominator, therefore the fraction is altogether smaller. If you want, you can go down further and you can get, n squared plus 2n plus 1 added to that one. So really this is 1 over n squared plus 2n plus 2 when all is said and done. But I don't think that that necessarily is as comparable as these two. It's not as easy to determine which one is bigger, in my opinion. I like looking up here where everything is otherwise equivalent except for the n term. Okay, so I'm going to get rid of that altogether. All right, so that means convergent. Moving on. The alternating piece may be hard to determine here, so I'm going to play around with some algebra that I am familiar with up to this point. For example, negative 2 to the n minus 1 is the same as saying negative 2 to the n and negative 2 to the minus 1, right? You can break that up. Think of it as a n plus negative 1. This right here really means that negative 2 belongs in the top. And we saw earlier that a negative product, a negative number in here can be broken up and in fact, whether or not this is on the bottom, it really doesn't matter. So I'm going to bring it out front. Why not? Not out front of the entire summation or series, but I'm going to put it right there so that we can clearly see that this portion is the a sub n sequence or series that we're going to be looking at. So first condition. What's the limit of negative 2n over 2 to the n? Well, both of these become infinity. In fact, the top becomes negative infinity, the bottom becomes positive infinity. So I'm going to apply L'Hopital's rule, take the derivative of the top and the derivative of the bottom. I now have a stationary top. It's static. Nothing's happening. And the bottom is growing. So my limit is 0. But what happens when I plug in n plus 1 everywhere I have an n? Is this still decreasing? So this is going to take a little bit of manipulation on my part. This is 2 to the n times 2, right? I can break that up and I can divide it actually with that 2. So I'm running out of space. Let me repeat what I'm going to do. This 2 to the n plus 1 is really 2 to the n times 2 to the 1. And that 2 can cancel with that 2. So now I have negative n plus 1 over 2 to the n and negative 2 and 2 to the n. The denominators are the same, but what about the numerators? If I plug in 1, I get negative 2 here, and I get negative 2 here. Okay, so at least at that number, they're the same. If I plug in 2, I get negative 3 here, and negative 4 here. This numerator is a smaller number. So in normal circumstances, this would be a smaller fraction. However, because they're negative, a smaller fraction is actually a larger number. So this one is divergent. Okay, let's say that you're not quite understanding this and you want a better, maybe not better way, but a different way to examine which one is actually better. What you can do is treat the n like an x. And I'm just going to type in, now I'm going to choose to type this in, but you could go as far as, the very beginning here. But I'm going to do negative x plus 1 over 2 to the x, and I'm going to compare it to negative 2x and 2 to the x. And I'm going to look at the tables and just compare which column is seemingly larger. I'm going to start at 1, and they're the same at 1. At 2, the left side is larger because it's less negative. At 3, the left side is larger because it's less negative. And that seems to be happening quite a bit. You can see that the term that I have here becomes the term here. So they differ by 1. We can already predict what's going to happen. And in each one of these cases, the left side is less negative than the right side, so the left side is larger. We don't want the left side larger. We want it to be decreasing. And in fact, because it's not, it's divergent. Last one before we take it to the next level. So again, if I'm looking at just this portion, first thing I do is take the limit as n approaches infinity of n plus 1 over n. The limit is 1. However, the limit is supposed to be 0. Because it's not, this already fails, and I don't have to go any further. It's a divergent alternating series. There's a little bit of a typo here. I want you to put in absolute values. There's a theorem that says if the absolute value of the series converges, then the series itself also converges. For example, if I look at this series and I already know it to be a convergent piece series, if it didn't have the alternating piece, then it itself would also be convergent. Okay, so if the positive is convergent, then it is convergent, which leads to the next topic. If we prove that it's convergent, like it was just saying, and the other one is convergent as a result, then we say that that's absolutely convergent. It's convergent regardless. But if we find that the absolute value is divergent, but according to the other two criteria for alternating series, if according to those it's convergent, then because we have a divergent for the absolute value and a convergent for the original, we call that conditionally convergent. Okay, so if both are convergent, it's absolute. If only the original is convergent, then it's only conditionally convergent. All right, so first thing I'm going to do is prove that it is convergent, if in fact it is. Starting with finding the limit of the non-alternating piece. Okay, certainly the limit of 1 over n to the 1/3 power, or the cubed root of n, is 0. And if I plug in n plus 1, then a larger denominator means a smaller fraction. Okay, so I know that it is convergent. But what I need to do now is take it a step further. What would the series absolute value around the original here? Now, what does the absolute value do? Okay, the absolute value eliminates the alternating piece because it won't be negative and positive, it'll be just positive. So we are looking at the series 1 over n to the 1/3. What do we know about that series? Well, this falls into the category of being a p-series. And according to p-series, if the exponent is between 0 and 1, then it's divergent. Okay, well, I already established that it's convergent. So if this second condition is divergent, then the overall convergence for this question is conditional. Okay, so in order to really do alternating series well, you have to be well prepared with the tests that we've learned up to this point. You can't really just go into 9.5 without knowing all of the previous lessons. Number 6 is an alternating geometric series, where it's a number raised to a power. You can think of these as just exponentials. They look very similar to that when we were doing those in Algebra 1 and Algebra 2. So first, is it convergent or divergent? Remember, take the alternating piece off, which means look at this as if negative 1 to the n was pulled out, leaving 4/5 to the n. All right, what would 4/5 to the n be? Now, I could break this up and I would get the, it actually looks very similar to a homework question that I actually now am thinking of the answer that I never completed. So 4 to the n over 5 to the n, all you need to realize is because the bottom is larger than the top, because this is bottom heavy, it doesn't matter what the top is, because this is bottom heavy, it's approaching 0. Now what happens when I compare 4/5 to the n plus 1 to 4/5 to the n? Well, I know that this is 4/5 to the n times 4/5. 4/5 is less than 1. If I multiply something by a number less than 1, then it's going to decrease in value. Okay, so according to the first set of circumstances, this is convergent. The second set of circumstances says, okay, now look at the series of just the non-alternating piece, the absolute value piece. Would this be a convergent series if it stood alone? Well, it's a geometric series, and your R value, I mean, I don't have to use absolute value here because it's positive, but the R value is a 4/5, which falls in between this category, or falls in this category. This is convergent. Specifically, it's a convergent geometric series. So if I put convergent with convergent, I get an overall absolute convergence. Okay. Keep going. Getting a little bit more difficult because we see a factorial here, but the same rules apply. First, take the limit. Okay. Which one's bigger? Well, to do this one, I think what I'd rather do is actually write out some of the terms so we can see what's happening. So the numerator is going from 1 to 2 to 6 to 24 to 60 to 1, hold on, 720, hold on. 24 is 4 factorial. 24 times 5 is 60 times 6. Wait, let me make sure I do that right. 5 factorial. By the way, factorial is found in your math button on the calculator. There's other places too, but okay, I did that wrong. So this is not 60. This is 120, and then this is 720. There we go. My denominators are growing by 2s, starting with 2, 4, 8, 16, 32, 64. And it doesn't take long to look at those fractions and realize the numerator is growing much faster than the denominator. Think about this. They both doubled here, but now the denominator is only doubling, but the numerator is tripling. Then it's quadrupling. Then it's quintupling. So the numerator is growing significantly faster. If this is divergent from the beginning, then I don't have to go any further. This is just divergent. Next one. First, what is the limit as n approaches infinity of 1 over the square root of n? And that's 0. Well, what happens when I plug in n plus 1? And hopefully at this point you know exactly what I'm going to say. A larger denominator means a smaller fraction. So we know that this is convergent according to the first set of criteria. However, what can you tell me about the non-alternating piece of the series here? So what can you tell me about the series 1 over n to the 1/2? Very similar to the one we did in the beginning, this is a divergent p-series. What I would look for on a test is not only telling me what series it is and what it is based on that series, but why. So this is divergent because the 1/2 falls between the 0 and the 1. Okay, in fact, I think this one is 0, 2, 1, and the 1 is included. So if I mix a convergent and then find that its positive absolute value is divergent, then my overall convergence is conditional. Okay, it's only convergent here, so it's only conditionally, it's only one-sided convergent, whereas it would be absolutely convergent if both were true. Okay, just a few more, or one more rather. All right, I'm going to challenge you to pause this, see if you can get somewhere on your own with this. If not, I completely understand, but yeah, just wanted to look at it on your own and not just depend on me all the time. So first thing we need to do is look at that numerator. -1 to the n times n plus 1 over 2. Is that going to alternate? Well, you know that one of these numbers is going to be even. N, if it's, say, 1, then this is going to be 2, so the 2 will divide with the 2, leaving just the 1, so it'd be 1 raised to 1, so that's going to be a -1. If I plug in 2, I get 2 and 3. The 2 here will cancel, and that's going to be -1 to an odd power. Wait a second, look at this. -1 to the 1, now this is if I plug in 1, gives me -1. If I plug in 2, I get -1 cubed, which is -1. If I plug in 3, I get -1 to the 6, which is +1. If I plug in 4, brain was not working there for a second. -1 to the 10, which is 1. If I plug in 5, bear with me here, get -1. Is that considered alternating? Well, just to double check, make sure I don't tell you the wrong thing. This is not considered an alternating series. Okay. This is not considered an alternating series. So if you remember the criteria, and this is what I was thinking to refer to, the criteria for an alternating series is that it has to be raised to the n, or the n plus 1. So basically every other term has to be 1 or -1. This is not changing every other term. But if we look at the absolute value part, so let's go back to that theorem that was mentioned right here. If we know that the absolute value converges, then we know that the original is going to converge as well. So let's see if we can figure out some convergence based on the absolute value. All right, if I look at this series and I put absolute value symbols around it, I end up with the numerator is going to be positive 1 regardless, right? If I take the absolute value of any one of those, I get positive 1. And I'm left with 1 over 3 to the n. You can also look at that as 1 over 3 to the n. This number falls between 0 and 1, so it's a convergent geometric series. If the absolute value is convergent, then I can say the overall original is absolutely convergent. So even if it's not alternative, but I'm able to prove that the absolute value is convergent, then I can prove that it's absolutely convergent altogether.